Hi, I'm Sanghyuk Lee, and I'm an MS student at Inha University, South Korea. Here I present an approach to enhance the few-shot learning performance of the meta-learning method by contextually scaling the backbone gradients. Meta-learning is well known as learning to learn. That is, the model first learns meta-knowledge through various types of tasks and transfers it to other novel tasks in test phase. By utilizing this meta-knowledge, the model can solve the novel tasks more efficiently. Meta-learning is usually can be categorized into three types by what to set as the meta-knowledge: metric-based, model-based, and optimization-based. Model-agnostic meta-learning, the most representative optimization-based meta-learning algorithm, sets an initialization theta as the meta-knowledge. From theta, the model can adapt to other novel tasks only in a few steps of adaptation. The problem of MAML we focus on is that during training, the gradient norm of the classifier is much bigger than that of the backbone. The figure below shows the gradient norm of each layer in log scale. The purple one belongs to the classifier. Also, the norm of the high-level convolutional layer is smaller than those of the other layers. This phenomenon implies that rather than learning how to extract task-specific feature representation, MAML tends to reuse the features and focuses on rearranging the decision boundaries. This phenomenon gets severe when the data domains differ. In order to solve these problems, we scale the gradient norm of the backbone in a task-wise and layer-wise manner. Our method consists of two parts: general CNN model f theta and a scaling factor generator g phi. To generate the scaling factors task adaptively, we adopt context parameters from paper number 1 to embed the task information in a vector form. Then we feed these task embeddings to g phi. After generating the scaling factors, we scale each backbone weight in fault path with the corresponding scaling factor. Because all layers are differentiable, we can train the model in an end-to-end manner. First, in order to avoid complicated scaling process, we use a batch normalization property. Most of the architectures contain batch normalization layers. Suppose we scale the weights of a convolutional layer. In fold propagation, the outputs don't change because the scaling factors are cancelled in normalization process. However, in backward propagation, the gradients are scaled by the reciprocal of the scaling factor. Furthermore, before scaling the weights, we normalize the weights, because by using the soft plus function in G5, the weights norm can increase without any upper bound. The generator G5 is a simple two-layer MLP. A value function is at between two linear layers, and a soft plus function is at the end of the architecture. Because G5 is differentiable, we can update context parameters in an end-to-end manner. It is updated by the equation below. Some may ask if there is any specific reason to use soft plus function. As mentioned earlier, the gradient norms are scaled by the reciprocal of the scaling factor. If we use sigmoid, the model only scales them in an increasing direction. If we use value, the training process can be broken. But if we use soft plus, we can make the model can choose either to increase or decrease the norm. Here are the quantitative results of our method. Our method improves MAML in a large margin, especially in cross-domain few-shot classification. The improvements get bigger, which shows the importance of the task-adaptive feature representations. For more results, please refer to our paper. In terms of gradient norms, our method facilitates the high-level layer to be updated rather than the classifier. So the model can extract more discriminative features than MAML. Here are the visualization of the feature representations. While MAML shows dispersed embeddings even after adaptation, our method shows improved intra-class compactness than MAML after adaptation. Our method utilizes task-adaptive representation by scaling the backbone gradients in a task-dependent way. As a result, our method improves MAML in various aspects. The code is available at the link below. Thank you.